let us look at automotive IoT applications. Okay, this is a hot topic. Many research groups, universities, R&D labs are working on this very hot area, and any amount of time we spend on this module is insufficient. Therefore, it is quite hard for us to cover anything in a limited time. However, if you have to build some, you have to start somewhere, right. So, let us assume that this module, at the end of this module, you will be exposed to at least do something by yourself with whatever resource that you have in front of you, and I assume that you have no access to any sensors. I assume that you have no access to any technology of any nature, but you have a good laptop or a home computer, and with this little resource you should be able to at least build algorithms, test a few algorithms and so on, right, which means many things have to be done in simulation, correct. So, we need a good nice simulator to, which is essentially a tool for you to work on this area. Now, what are the hot problems in this area? What is it that people are trying to solve in this area of automotive applications? Let us go at least, I would say 15 years back, okay, 15 or even 20 years back, when the first attempts at anything related to autonomous actually came into picture. The whole area of autonomous driving or autonomous way of transportation or intelligent transportation actually did not start so much with automobiles, but was really fueled by airplanes. Autopilot in an airplane, not so famous today due to several recent crashes of the airplanes, is not a very popular thing today, right. You have problems related to angle of attack sensors malfunctioning, reporting wrong values and so on and so forth. So, they are all issues which are tightly integrated into the autopilot, but nevertheless landing of a plane is by and large because of autopilot. Safe landing, all the safe landings that have happened today are actually under very harsh weather conditions are because of autopilot, which means man has all the time thought about how can I leverage a technology in a manner that it will benefit us. So, IoT is the best example of that, right. You have some set of sensors, you have set of end effectors, and you have human in the loop, and what else it should create a lot of magic. So, that actually, so autopilot is already very mature. Several versions of autopilots have been released. Airbus has its autopilot, Boeing has its own autopilot doing several functions of the plane. So, in that sense autonomous flying is around. So, if you now apply autonomous flying to autonomous driving on land, it is not the same ball game. For instance, at least today or at least I would say 20 years ago, the possibility of two airplanes colliding was first of all there is an algorithm which will take care of ensuring that two planes will never have a collision at the cruising altitude. There is an algorithm built into the planes, and planes can actually detect and then take some decisions. That is also something that the autopilot actually does. There the problem of collisions is not so much, there is so much of airspace, and there are no problems of obstacles. If at all there is an obstacle, it is another plane perhaps. But then there are issues of turbulence and other related issues which the plane has to worry about, oxygen supply inside the planes and so on and so forth. Problems there are of one type, problems on the ground are a different type. You have obstacles include humans, trees, cattle, right, and major accidents happening because a dog crosses. So, you have to detect at high speed dogs cross, there is wildlife, so many things. So, the ground related problems of autonomous driving are the set of issues are completely different compared to, let us say, an autopilot of an airplane. But while the idea of autonomous is around, The problems are different because the domains are completely different. Now if you just say I have a car with me and what is the minimal thing I want to do with this car in front of me or a four wheeler in front of me, and I want to do some very simple things, right. So simple automations that I want to do. Today a modern car actually does a lot of it, right. For example, when you are backing, you have a screen in front of you and there are sensors behind which actually detects that you are hitting close to a wall or you are close to perhaps a water gutter or something that will create a problem for the car and things like that. So a lot of nice things are already out there. You start putting all these things into a proper perspective, you realize that there are actually good standards which will tell you that there are different levels of automation that you can talk about. These are called ADAS levels. There are different levels of ADAS. I think the highest level indeed is 5. So that is really highest level of autonomous driving. So let us not worry about, let us not get into that, but you just have to note that there are levels at which one can talk about the complete automation or autonomous driving applications. Question is, given this large space, where does IoT come into picture? What are those IoT sensors and what are their issues and what can we do given this limited time in front of us? I want you to look at what I have written on screen here. Look at the screen here. Here I have shown a 2D representation of an automobile. So there are only 2 wheels, I did not want to show the other part, and then there is a steering and there is a driver, and then some sort of a link going out which is trying to look for objects essentially, and to see whether these objects are actually obstacles for us or not. So first is to do what is known as objects, to check if there are objects in front of us, which is essentially doing object detection, then leading to saying whether it is indeed an obstacle or not an obstacle. Very simple. Look at just how you are driving in the most natural way. As you keep driving on your steering on the road, you have the road, you have vehicles in front of you, you have vehicles on the left and you have vehicles all around you, then you have trees, right. There are some trees and there are so many other related things. They are all objects which the eye is seeing. Now how many of them are really obstacles is the second part. If you are very close to a car in front of you or a two wheeler in front of you, then it becomes an obstacle for you and you have to brake, you have to do so many other related things. Otherwise you keep driving, you are just objects which the eye is absorbing. So quite like that, there are a lot of objects. So you have to go and classify different objects. You have to go and say that this is a tree. You actually, when you are driving without your knowledge, you are actually doing that. You are saying this is a tree, this is a two wheeler. The space occupied by the two wheeler is of one nature compared to that of another four wheeler in front of you. So you are classifying different objects. Brain is actually doing all that by using eye as a sensor, and it is trying to lay a 3D map in real time, right, and then only then you are very successful in driving without any accident. So you have to do all of that as a first step. So what kind of sensors can one think about? Again I want you to look at what exactly people do. These sensors essentially you can have ultrasonic sensors, you can have a radar for automotive applications, you can have a camera for automotive applications, and you can also have lidars as part of sensors for both object detection and then leading to obstacle detection. Now when should I use what is a question. So I put down this little chart, it is a very high level chart. I am not written down anything very technical here, but just because I just want to introduce you to the possible range of sensors. Take ultrasonic. In ultrasonic, these are essentially simple sensors, very reliable sensors, cheap sensors, and they are typically used even today for detection of when you are backing the car, right. You could be using simple ultrasonic sensors, and they will give you a signal and they will tell you what is the range between the car and the obstacle. They will give you warning, actually they will give you signals, and the whole IT system that is built around the electronics of the sensor actually gives you all kinds of enunciations like audio and all that. So you build a lot of intelligence around these basic using these basic sensors. Only thing is they are restricted, they are very short, and they can't really distinguish and tell you what that object is. It can't tell you whether it is a let us say a sort of a wall which is an obstacle for when you are backing the car, or whether it is a human that is obstructing it, or is it just a stone, or whether it is a water you know, for storm water drain essentially, which is you know, at a slightly elevated height. You will not be able to make out any of that. So that is really an issue. Look at radar. Radar for automotive applications very mature. You have pulse Doppler radar, you have FMCW radars, they are used for both long as well as for short range. They can be used, again it is hard to do anything with them with respect to knowing what that object is. So that is also, but it is indeed one of the important sensors which are used in autonomous and automotive applications. Autonomous is one part, automotive radar is an important thing. So the radars we have to spend time in understanding how the automotive radar works. So we should look at the range, we look at frequencies of operation and so on. Then of course camera is very good because it can tell you by looking at the picture, you can do some simple image processing, video processing, and actually find out what that object is, and therefore that is pretty good. LiDARs are around for a while now, there are some things which are used in autonomous driving. They are indeed both long and short range. There have been university efforts in trying to understand, to look at what that object is using LiDARs, but it appears to be a very hard problem to do object identification using LiDAR data, right. When you talk about LiDAR, immediately what should occur to you is it a single line or multi-line LiDAR? Okay, so you have to note this, unless you have multi-line 64 line radar LiDAR, your reconstruction under all possible scenarios will be very difficult. So you must look at multi-line LiDAR systems. Now all of this essentially means fine, very good, you have good sensors, you have extremely good sensors which cater to different range requirements and so on and so forth, but what is a good algorithm? How do you do object detection and obstacle avoidance if required, right. So these things have to be, you have to really lay emphasis on those basic algorithms which you should use. Before I go into the detail of this these algorithms, it is good to see two demonstrations, but before I do that demonstration, I am going to add an additional dimension to this discussion. Okay. Look at these 4 sensors that I have put here. Okay. These are the 4 sensors: ultrasonic, radar, camera and LiDAR. How good are these sensors? How good are these sensors if there is another automobile, okay, which is perhaps also on the same path. Okay. So they will also, this automobile 1 and automobile 2 both are equipped with these sensors, one or many or all sensors, let us say. Question is, what can you do if there are 2 automobiles? Okay. This indicates that they are about to sort of collide into each other, but that is just a representation. I just wanted to show you that another vehicle is there, which means, or for not scaring you in the first class, I will erase this here and I will put it next to this. Okay. This might help you to complete the course without worrying about major collisions and accidents and so on and so forth, right. So this is another vehicle very next to it. Now these sensors are not really these are sensors for getting information inside a vehicle. What if you had a wireless link between the two of them? What can you do? What kind of nice things can be achieved is the question, and I am sure you will be able to replicate this demonstration quite easily on your own laptops and on your own computers. Complete source code will be given to you, you can build it on your own. First exercise which will help you to get started on this system by playing with the code that is made available to you. Think of a scenario which is like two vehicles which are trying to approach from two tracks, okay, and there is an intersection here, and there is a vehicle from this direction, there is a vehicle from this direction. So, I am just preparing towards the demo, okay. So, there are two vehicles, and the idea is without colliding and without but using communication between them, the two vehicles should cross each other. One simple thing is, if I am able to communicate the distance, no, rather the current location, the speed, current location and speed, then by passing this information I could come out with a simple algorithm which will allow this vehicle, perhaps because it is closer to the intersection, not to cut speed, but this vehicle perhaps either cut speed or completely shuts down, or sorry, stops, allows this vehicle to pass and then moves over. What will this do? What will this experiment do? It is something very simple, right. Good thing is you can get rid of traffic lights. You do not need traffic lights anymore if you do this, right. There is no way by which you need red and green anymore if this communication between vehicles happens. If the first vehicle here, let us say if there are multiple vehicles behind, if the first vehicle and the first vehicle on either direction is able to communicate and that information is passed on to all the vehicles that are behind the first vehicle, then you have a nice scenario of not even having a single traffic light anywhere in the city. Doable? Well, I think it is doable, and our goal should be to attempt something like this towards building a application of that nature. What does all of this, what does it mean? It means what I have written here. The whole area of automotive work that you want to do is about algorithms. What are good algorithms? You have to study those algorithms, okay. If you understand the basics of these algorithms, build these algorithms, then you have a framework for building automotive IoT applications. So, this course, this particular chapter indeed is highly algorithmic by nature, okay. Having given you this background, without wasting any more time, let us see a demonstration on a simulator. What that simulator is, all of that I will handle separately soon after you see the video. But this simulator is this video that you see here is also a little bit, I would say, hilarious, and I am sure you will appreciate where that fun element actually comes from. Let us see the video. Let us see the problem. The problem is pretty straightforward. There is a need for this robo to move forward, correct, in this direction. As you can see, the arrow is pointing in this direction. The other robo has to cut across, so it is an intersection, right. There is a T or a L, I would say, it is a T perhaps, actually it is a cross, more like a cross, right, it is like a cross. This screen here, yes, okay, it is like this. So, you want, one vehicle wants to go this way, the other vehicle wants to go this way, alright. So, good. Now, you look at this object, back to this screen here, this robotic system, this is an automobile, okay, and you can see there is something popping on top, there is something sitting on top here, there is something sitting on top there. these two essentially are nothing but communication devices, communication modules, and these communication modules essentially are sort of the ones that are used for communicating the current location and the speed at which the vehicle is moving. So, let us start the video and see what actually happens. There you are. There you are, that is the fun element. You can see that both the vehicles have dropped out of the screen, and that is the fun part. So, you saw that nice demonstration in a simulation environment, right. It was quite hilarious. The two-wheeled robots that you saw on either side, they just dropped off after the platform, right. Clearly those situations were not handled in the simulator, and often it should not happen that when you put your algorithms in place, that these autonomous cars or these things should not just drop off go off the road or drop off a cliff, right. So, that is where the real trick is. How do you plan everything for your vehicle in a manner that it moves in a coherent way, in a coherent manner, and it is able to reach its destination. Okay. So, if you have seen the demonstration, you may also be wondering what is that simulator, what is it doing and all that. So, for that I wanted you to get introduced to this simulation environment simulator called VREP. Okay, I have written it here. You can see that VREP stands for Virtual Robot Experimentation Platform, and this is essentially from a company called Coppelia Robotics. This is the name of the company, and this company essentially is giving away this robotic platform, simulation platform, free if you are an individual or you are a student or you are part of an educational setup like a university and so on. So, as far as this course is concerned, if you are representing yourself as a student of this course, I think there are no issues in downloading VREP, installing it on your laptop and experimenting with VREP. Okay. But if you are part of a company setup, you have to be very careful, read the license which is out there very clearly, ensure that you are not violating a single rule as mentioned by the company. So, I am assuming that you are students of this course, and therefore, this is okay to download and experiment with, alright. Now, what is this VREP? VREP is an IDE, essentially integrated development environment. It is based on some sort of a distributed control architecture which the company themselves have put in place, and here each of the objects that you see within a simulation environment, it could be sensors, it could be controllers, it could be end effectors, whatever be the objects which are within the simulation environment, each of these objects, which is nothing but a sort of a model, even if it is a model, they can be individually controlled, and this control can happen in many ways, very many ways. One is you can control through an embedded script, you can control through plugins, you can control through interfacing through robot operating system or ROS, or BlueZero and remote API, which is also a very important requirement. So, this BlueZero, maybe you may be wondering, BlueZero essentially is a cross platform. So, let me put it down here, or maybe go take the next sheet. BlueZero. So, BlueZero is interface is essentially for, it is a cross platform middleware. Okay, it is a cross platform middleware for I would say for interconnecting for interconnecting several pieces of software. Nice, interesting kind of a cross platform software, and you can be running it in multiple threads, in processes and all that, and it has quite some similarities to ROS. Okay, so there are quite similar to ROS, but its main focus appears to be on communication paradigms. If you want to know more about this, you should do the first course on design for IoT, where we talk about client server as well as publish subscribe. Okay. Typically MQTT, then AMQP are all part of publish subscribe, and CoAP kind of protocols essentially form the client server kind of paradigms, right. Basically all the RESTful architecture, REST API. So it's seemed to be concentrating more on the communication paradigm. Now in VREP, any controller that you design can be coded in several languages. Java is supported, C is supported, C++ is supported, Python is supported, okay, and Lua, which is also very native to VREP, Lua, L-U-A, Lua. Lua is supported, MATLAB, Octave, OCTAVE, Octave. Okay. So this is in brief about VREP. There are several videos on how to install VREP, how to work with VREP, how to set up a first experiment in VREP, and so on and so forth. So you could look up any of those videos, and I think it will be a repetition if we sort of do all of that here. Instead worry so much more about our own example on automotive IoT applications. But nevertheless, if you want to start somewhere, how do you, by just looking up the videos may not help you in this course. So what we will do now is we will take a very simple drag and drop kind of application. We will just take a few objects, connect them together, and put back this interesting demo we saw under VREP. Okay. So let us start with that, and to that let us now move on to VREP simple drag and drop application. So I am assuming that this screen you will get soon after you install it on your laptop, okay, and all of that is set. Now what I suggest is you should first go and take a new sort of a scene, okay, take a new scene. So you are ready now, and you will now go to basically the model browser, go to the model browser and pick a mobile robo, okay, pick a mobile robo, which is perhaps called Pioneer, right. By the way, it is important for you to realize that if you see a Pioneer P3DX kind of a robo, you can be more or less sure that you can physically buy Pioneer. Okay. Most of the models in VREP are essentially those components which essentially are available as either robotic platforms, end effectors, sensors, and so on. So all these are nothing but software components. Okay. So if you can't invest in a physical purchase of a Pioneer robo, buy this install this VREP simulation software, and then you try out in all the applications within that system. Now look carefully, we want this scenario, right. you want one robo to, let me go back to the screen here, that will help you to understand what is critically required. You have one path like this and another path like this, right. So, you want one robo to move in this direction and you want the other robo to move in this direction. Now, go back to the VREP demonstration. You see that both the one robo appears to be good, the one here appears to be good, it is moving in, it is going to likely to come in this direction, but this robo requires a rotation, otherwise it would go parallel to this in the opposite direction. Therefore, now you need to go to the tool browser and pick the rotate, right. You see the object there, you rotate it and you rotate it by 90 degrees. So, now you have rotated it. Once you rotate it, let us understand what this Pioneer DX robo is all about. It actually integrates ultrasonic sensors. So, let us go back and put this system here. You have a robotic platform, you have a set of ultrasonic sensors in the front and you have a set of ultrasonic sensors at the rear side. There are 8 in the front, 3 plus 3 6 plus 1 7 plus 1 8, okay. And then there are 8 3 4 5 6 7 8, okay. There are 8 on this side. So, this is one part. Then there is also a requirement. So, we will also have to sort of use the other part is that what we should do is we should add another component which is essentially the wireless transceiver part. So, let us put that wireless transceiver, okay, go down and pick this wireless transceiver and associate this wireless transceiver as part of this robot, okay. So, essentially you can think of this as a parent, the robot as a parent and the transceiver as a child of this parent. So, this association is being done now. So, let us complete this. So, they are now part of one unit and should we place it on top? Let us move it on top. Let us move them on top. They are now part. So, there is one parent and one child, another parent and another child. Okay, that is good, and take that. And place it there, right. Okay. Now, look carefully at the Pioneer robo. You see on the front side the ultrasonic sensors that are shown, behind are also a set of ultrasonic sensors. Now, what we will do is we will essentially run an algorithm. What is actually happening? You can see now that quite similar to the airplane example we took, no two planes can collide at cruising height, cruising altitude. They come extremely close, dangerously close, but decide to take two separate paths very intelligently and just move away from each other, perhaps in the plane case changing their directions and also the altitude, so that they are not in the same plane anymore. Two planes are not in the same plane, perhaps that is what the algorithm actually does. In this case, what is that algorithm? You can see on the left side there was a flash of hello world, this is my number 232, hello world, this is my number 233. Why did this happen at all? Because transceivers were in the range, and they realized that they are within the range, but they did not know how close they are. Okay. So, one is being in the range, the other is to actually estimate the how close they are in terms of applying a sort of a threshold, and once they come within a threshold distance, they need to kick in this algorithm and decide in a manner that they do not have a collision, right. This is the key point.